A monkey hitting keys at random on a typewriter keyboard for an infinite amount of time will almost surely type any given text, including the complete works of William Shakespeare. Hello and welcome to Almost Sure, a channel about mathematics with a skew towards probability. But we're not going to shy away from any subject area, so don't be surprised to see posts in the future on analysis, on number theory, or any other area of maths. For now though, consider repeating the same action over and over again, randomly generating output at each step. Then, roughly speaking, and given enough time, anything that can happen will happen. But how long can we expect it to take? Well, there's a particularly nice way of calculating this, and much more besides, using Martingale theory. And the answers actually just kind of drop out from looking at simple gambling strategies. And that's what I will look at here. Back to our monkey, typing away at the typewriter keyboard for ever and ever. This generates an endless sequence of characters, and if we suppose that each one is typed entirely at random and independently, then according to probability theory, then yes, it's true. Any given sequence does indeed occur with probability 1. For anything beyond just a few words though, the expected time can be, well, astronomical. It was the best of times. It was the blurst of times, you stupid monkey. Okay, let's put this into some context. A bit of Googling tells me that the complete works of William Shakespeare contains about 3.7 million characters. Now let's suppose our typewriter has 26 keys, one for each letter of the alphabet. Okay, a real typewriter can have more than 40, but we'll keep things simple and just ignore all of the characters, just looking at letters of the alphabet. Now if each key press is entirely at random, then the time to type Shakespeare is, on average, about 26 raised to the power of 3.7 million. Now this is a number with over 5 million digits, which is just unimaginably huge. Just writing the number down would fill a book longer than the collected works of William Shakespeare. In fact, the longest lived monkey is apparently its cheetah from the Tarzan movies, and he lived to the ripe old age of 80. Even if he spent his entire life typing at a rate of 10 keys a second, then this is only about 25 billion key presses. Okay, that sounds like an impressive number, but it doesn't even make a dent on the number we need here. In fact, even if every subatomic particle of the known universe was a tiny monkey, typing away, starting at the Big Bang, all the way up until the heat death of the universe, then we still don't even make the tiniest dent on the number required. In fact, the number of universes required would still be a number with over 5 million digits. So it's just impossible to comprehend or explain the size of such a number. One thing that we can be sure of though, that's no monkey is ever typing the complete works of William Shakespeare. Or at least, if a monkey ever does type the complete works of William Shakespeare, then it's not by random chance. How about something a little bit simpler? How long does it take the monkey to type just a single word? How about typing the word abracadabra? Now this is 11 characters long, and we can expect it to need about 26 to the power of 11 key presses. This is still a huge number to be sure, and furthermore it's just an estimate. In fact, the exact value, I can give you this right now. It's 26 to the power of 11 plus 26 to the power of 4 plus 26. Now this number might seem a bit mysterious, but if you know the Martingale technique, then it's actually pretty simple. Now going through it, unsurprisingly, the reason we have powers of 26 is from the number of letters of the alphabet. And looking at the first term, now this is raised to the power of 11, which is because abracadabra has 11 letters. So far, so simple. Now let's look at the other terms. These appear because the start and end of the word abracadabra have some parts in common. In particular, the first 4 letters and the last 4 letters, they're both the same. In fact, they're both abra. And this can cause some overlap in the ways that abracadabra can be typed. And the monkey could type abracadabra twice in a row, or it could overlap them. And this actually increases the expected time for the first appearance of abracadabra. And this gives the 26 to the power of 4 term. And then moving on, the single letter A appears both at the start and at the end. And in a similar way, this leads to 26 to the power of 1 term, or just 26. Now, admittedly, this probably still seems mysterious, but stick with me. If you pay attention to this video, then, well, hopefully, it should all become clear. By the way, I didn't just pick this example at random. In fact, it appears in a fantastic book by David Williams called Probability with Martingales. And I have my copy here. It's highly recommended if you want to learn martingale theory. And you can tell by the yellowing of the pages here that I've had this copy for many, many years, but it's still a classic. And it contains exactly this example that we are discussing about the monkey typing abracadabra. I'll get back to this example in a moment. But for now, let's try making things even simpler. Consider tossing a coin. Now there's only 2 possible outcomes, heads or tails. How long to get 1 head? Now the answer, well, of course it's random. So I'm talking about the expected number of tosses. And let's assume it's a fair coin. So each toss, heads and tails are equally likely. Now the answer to this one is easy and you probably know it. It's 2 tosses on average. But before looking at using the martingale approach, let's try and get a bit of intuition for what's going on. For any sequence of independent trials with a probability P of success on each go, this requires on average 1/p attempts. This is just a well-known fact and is a property of the geometric distribution. So for a fair coin, where heads has probability P is equal to 1/2 of occurring, then we have expected time of 1/p is equal to 2. We can, if we like, compute this directly from working out its distribution and then using this to compute the mean. I won't talk you through this calculation now, as I'm going to explain it using the martingale method soon anyway. But if you are interested, you can check out the calculation, which I'll display just here. And, well, pause it or slow down the video if necessary. In addition, there's also a neat Markov approach, which I'll also display here. This uses the fact that if you don't get ahead on the first toss, then the expected remaining number of tosses is still the same as when we started. Because if we get a tail on the first toss, then it doesn't change the distribution of any of the future tosses. And this gives us a recurrence equation which you can solve to get the same answer again of 1/p. In any case, this idea applies quite widely. For example, rolling a dice takes 6 goes on average to get a 6, or our monkey sat at his keyboard, he takes average 26 key presses to get any given letter. But what about the expected number of coin tosses to get 2 heads in a row, or to get a head followed by a tail? Which of these 2 do you think takes longer on average? Do you think they both take the same? Or do you think one takes longer than the other? And if so, which one takes longer and by how much? Well, before actually getting into this, let's try and estimate it using a simple intuitive idea. So suppose we get this sequence: tails, tails, heads, tails, and so on. Then we can group this into overlapping pairs of tosses like so. In this example, we see there are 6 tosses before heads heads comes up, which is 5 overlapping pairs. And similarly, they see that there are 4 tosses for heads tails, which is 3 overlapping pairs. And in general, the number of tosses is 1 more than the number of overlapping pairs. And each pair will have a probability p is equal to a quarter, or 25% of being heads. Similarly, p is equal to a quarter of being heads tails. And as before, with a single head, you could just guess, right, that it takes on average 1 over p is equal to 4 pairs. So 5 tosses on average to get heads, or indeed heads tails. But this is ignoring something very important, which is independence. When we looked at individual tosses, each one was assumed independent of all previous tosses. Regardless of what's happened so far, the next toss always has probability 1 in 2 of being heads. But adjacent pairs of tosses, as we have here, are overlapping, so they're not independent. And in fact, the second toss of any one pair is always the first toss of the next pair. So if we have a tails, then the next pair starts with a tails. Or if we have tails heads, then the next pair starts with a heads, and so on. This means that if we get heads tails, then the next pair starts with a tail, so it can't possibly be another heads tails, which means we cannot have consecutive heads tails, meaning that they are, well, effectively they're negatively correlated. And on the other hand, if we get 2 heads in a row, then the second is a head, so we only need 1 more head to get another 2 heads in a row, which means that we are more likely to get pairs of consecutive heads or double heads than if they were independent, meaning that effectively it's positively correlated. So here's a question for you. What effect do you think this correlation has? Do you think the positive correlation of pairs of heads increases the expected tosses above our rough estimate of 5, or decrease it? Does your intuition help here? In fact, let me tell you, it does increase it. Getting heads takes on average 6 tosses, and getting heads tails reduces the expected number of tosses to only 4. Maybe your intuition helped here, or maybe it didn't, but let's think about this for a moment. The positive correlation for heads means they are more likely to be bunched together, leading to a longer waiting time for the first one. And this is just like the old adage, right? That you wait ages for a bus and then 2 come along at the same time. And everyone understands that this is a bad thing. But why? Well, because if buses arrive in pairs, you need to wait longer on average to get the first one. And it's exactly the same intuition here. On the other hand, the negative correlation for successive heads tails means that they are more evenly spaced, reducing the average weight to only 4. Now there is a simple method to exactly calculate the answers that I just mentioned. It's kind of an ad hoc method, but let's go through it. Starting with the expected tosses to get heads tails. The idea is that we first wait for a head to appear. This is 2 tosses on average. Then we wait for the first tail following on from the first head, another 2 tosses. But the first tail following on from the first head, well, this must be preceded by a head, meaning that it is just the same thing as the first heads tails. So what's that? Number of tosses to get heads tails, then is 2 for the first head, plus 2 for the next tail, 4 on average. Now we can do something very similar for expected tosses to get heads, but it's a little bit more complicated. We start in the same way, right? We wait for the first heads, so 2 tosses on average, but then we do 1 extra toss. If it's heads, we're done. If not, then we start over. And we keep doing this until we get a head, and then the extra toss is also a head. So this splits the sequence into these shorter sequences, where each shorter sequence is the time to get ahead plus one extra toss. So these are of length 2 plus 1 on average. Now we're going to be done as soon as this additional toss at the end of one of the short sequences is ahead. So on average we have 2 short sequences of length 3 on average, meaning that the total number of tosses is 2 times 3 or 6. Nice. But let's write this out mathematically. We can break up the calculation by first conditioning on the number m of short sequences, then take the expectation of this. And as claimed, this gives us the expected time to get aheads plus 1 multiplied by the expected time to get heads. So 3 times 2 or 6. But what about, let's say, 3 heads in a row, or heads, tails, heads, or heads, tails, heads, tails? How long can we expect to wait for any of these to appear? Well, I can actually compute the expected number of tosses for each of these just in my head. For example, heads, 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 this is going to be 8 plus 4 plus 2 is equal to 14 tosses on average. Heads, tails, heads is 8 plus 2 is equal to 10. Heads, tails, it's 16 plus 4 is equal to 20. Now, you might ask, you could well ask, how can I just state these off the top of my head? Is it some kind of wizardry, or am I cheating? Did I work them out in advance? Well, okay, yeah, the video is largely scripted, but that's not the point. The point is that this is where the magic of martingales comes in. So, let's get started. Let's make this interesting and make a game of it by introducing some cold hard cash into the equation. Suppose that we can bet on each coin toss. I bet $1, and if I correctly guess the outcome, then I win $2 back, which is $1 plus my stake back. Whereas if I guess incorrectly, then I just lose the stake. Now we can do this for a biased coin with probability P of heads. There we would need to win back 1 over P for a fair game. But I'll assume a fair coin in this explanation, so P is equal to a half. Now, this is a fair game. We have 50% chance of winning $1 and 50% chance of losing $1. So it's 0 on average. Now let's bet $1 that the first coin is heads. If it isn't, then we'll bet $1 that the second coin is a head. And if I lose again, then I'll bet $1 that the third is a head. And so on, until eventually a head comes up and I win and I stop. So let's look at this example. So take it away. Now, this is a net loss of $2 in this example. But what is my profit and loss in general? Well, if a head appears on the nth toss, then I have staked $1 a total of n times. But I only won once when I predicted the final head, in which case I received the $2. So this is a total net profit of 2 minus n. But it's a fair game, which means that our net profit must be 0 on average. So expected value of 2 minus n is 0, which we can rearrange to get expected value of n is equal to 2. Simple. Now it's well known that the number of tosses for the first head is a geometric distribution where the probability of it equaling n is a half to the power of n, and this can be used to calculate the mean, but we computed the expected value without even using this. Just the idea of looking at a fair game gave us a shortcut to the expected number of tosses without even thinking about the full distribution. Now, the net profit of a fair gambling strategy like this, at each time step, it forms a kind of process, which mathematicians call a martingale. Now, the very nature of such games means that our net profit is random at each time. So martingales are a type of stochastic process. I will look at the maths of martingales in a follow-up to this video, but for now, let's develop these ideas of simple gambling strategies a bit further. What about two heads in a row, or heads tails, or heads tails heads heads, or any other finite sequence? How can martingale theory help us here? Well, let's consider heads tails to start. And as before, we're going to bet on the coin tosses. We bet $1 that the first toss is heads, so if we win, then we get $2 back. In which case we will roll this over to bet that the next one is a tail. And what this means is that if heads tails comes up straight off the bat, then we get $4 back. Otherwise we get nothing and we just lose the $1 stake. Next, consider a whole team of people arranged in a line. And the person at position N in this line is going to apply the strategy that I just mentioned, but starting at toss N. So he's going to bet $1 that toss N is heads, and if he wins, then he takes the $2 and he rolls it over to bet that the next one is a tails. So let's see how this works. Now let's consider the total profit and loss of everyone betting. If heads tails comes up on the nth toss, then n people have entered the game so far. They've each staked $1, so that's a total amount of n dollars staked. But only one person here has any winnings, and well, that's the person in position n-1 because they correctly predicted when heads tails would come up, and they have $4. So this gives us a total net profit of the $4 winnings minus the n staked of 4 minus n. And this is a fair game, so the expected profit is 0, expected value of 4 minus n is 0, or rearranging this, expected value of n is 4. So 4 tosses on average to get heads tails, which we know already, but we now have a nice martingale proof. But what about heads heads? Well, this can be looked at in a similar way. So we consider the same situation with a line of people all betting on the coin tosses. But this time, the person in position N, they bet that the nth toss is heads, and if they win, they roll over their winnings to bet that the next is also a head. So let's see how this goes. Again, let's look at our total profit and loss from the game. When heads heads eventually appeared after n tosses, then as before, n people have entered the game. They've each staked $1, so again, n dollars has been staked. And person n-1 wins $4 as before. But now we have an additional winner. Person n also has some profit. Although they did not predict the full sequence of heads heads, they're still in this game. They bet that heads would come up on the nth toss, and it did. So they have $2 winnings that they have not yet rolled over. So we have a total winnings here of $4 for person N minus 1 plus $2 for person N, $6 in total. This gives a net profit of 6 minus N, and again it's a fair game, so 0 expected value, which gives expected value of N is equal to 6. Pretty cool, right? And again we note that this is larger than what we got for heads tails, and we should also be able to see another reason why this is the case now. It's precisely because it starts and ends with heads. If we are betting on heads for each pair, one toss at a time, then we get more winnings. And this more winnings must be compensated for by more stake, which means more tosses on average. So now we've seen the Martingale method applied to coin tosses. But the beauty of this idea is that it applies to any sequence of independent events. So consider, for example, a regular dice. How many rolls does it take, on average, to get 2 6s in a row? By now, you should be able to see that this is just 6 squared plus 6 equals 42. But let's go through it. On each roll, a player bets that 6 will come up. And if they win, they roll over the winnings to bet that the following roll is also a 6. So this means that if they stake $1, then if double 6 comes up, they win $36. So let's play this game. So looking at our total winnings in this game, then we have the one player who correctly guessed the double 6, who wins $36. And then we have the final player who correctly guessed the final 6, who won $6. So that's $42 in winnings. And as before, the fact that this is a fair game and each player is staking $1, we have an expected number of rolls of 42. So hopefully you can see the pattern now. The expected time to roll 666, for example, would be 6 cubed plus 6 squared plus 6, which comes to 258. On the other hand, the expected time to roll 656 would be a little bit less. It would be 6 cubed plus 6, which comes to 222. Let's return to our monkey, typing away at the typewriter keyboard. How long does it take to type abracadabra? Now you should be able to see where we're going. And we suppose that he presses the keys at random. We only count the 26 letters of the alphabet and we ignore any other characters. So we're going to have this whole row of gamblers where one enters the game before each key press, and he will bet $1 that it's A. If he wins the bet, then he will roll over any winnings to bet that the next character will be B, then that the next character will be R, and all the letters of abracadabra in turn. And each correct guess will multiply the stake by 26. At the end, when the monkey eventually types abracadabra, then one person has correctly predicted the whole word, and they win a huge 26 to the power of $11. One person predicted abra, and they win 26 to the power of $4. And the last person to enter the game predicted the final A to win $26. As N people have entered this game, each paying $1, as it's a fair game, then expected value of N is equal to the total winnings of 26 to the power of 11 plus 26 to the power of 4 plus 26, and we're done. Admittedly, if you just use the simple guess of 26 to the power of 11, then although wrong, you would be very, very close, relatively speaking. It's only out by about 100th of a millionth of a percent. But we're looking at a very general and exact method here, which applies quite widely. The expected time to type abracadabra is actually a well-known application of martingale theory from the book by David Williams that I mentioned earlier. But there's also videos here on YouTube, so I'll leave some references in the description below. But the ideas are actually much more flexible than just this. Consider our previous game, so let's bring that back. Now let's modify it. So rather than each player betting a stake of $1, the first bets $1, the second bets $2, the third $3, and so on. So now the nth player is betting N dollars. Otherwise, the game is the same as before. But now, when abracadabra comes up after N key presses, the total amount staked will not be N. It will be 1 plus 2 plus 3 plus all the way up to N. Now, this is a well-known sum, equaling a half of N times N plus 1, or N squared over 2 plus N over 2. Now, here's a question for you. Using the fact that it's a fair game, can you use this expression to compute the variance of the time to type abracadabra? I'm going to leave this as an exercise for the, motivated viewer. Not because I want to avoid doing this. I want to move on and do something even better. Let's look at something called the generating function. The generating function of a random variable n is, it's just the expected value of t to the power of n, which is a function of this parameter t. You can choose t between 0 and 1 to ensure this is well defined. So we have a function of t, but this actually encodes the whole distribution of n. What we do is we just write out the generating function as a power series. Then the probability for each value of n can be read off from the coefficients of the generating function. And we can do more. We can compute all the moments of the generating function by repeated differentiation. So really, the generating function is just a convenient representation of the distribution. So back to our game. Each gambler is betting that abracadabra will come up, starting on their turn, by betting on each letter in turn and rolling over any winnings. But now suppose that the first gambler bets $1 as before, but the second bets t dollars, the third bets t squared dollars, and so on. So now the nth person is betting t to the power of n minus $1. So how does this change things? What is the profit and loss now? If it takes n key strikes to type abracadabra, then the total amount staked will be 1 plus t squared plus so on, up to t to the power of n minus 1. You should recognize this as a geometric series, so we can just plug in the usual formula for a geometric series to get the total amount paid. And looking at our total profit, we're in the same situation as before, where there are 3 winners, and each one has their winnings scaled by their stake, which is now t to the power of n minus 1. So for the 11th to last person, they correctly bet on the full word abracadabra. So they win their stake of t to the power of n minus 11 multiplied by 26 to the power of 11. For the fourth to last person who correctly guessed Abra, their winnings are 26 to the power of 4, but now scaled by t to the power of n minus 4. And then for the last person who correctly guessed just the letter A, their winnings are 26 scaled by t to the power of n minus 1. So writing this out, let's extract out some common t to the power of n terms to simplify this a bit. And it's a fair game. So total winnings equals total amount staked on average. We can rearrange this, extract out expected value of t to the power of n terms and collect these together. And we've done it, hurrah! Using the idea that the net profit of a fair game is 0, we have found the generating function for the time to type abracadabra. So we have the distribution. And as we previously mentioned, we can now use this generating function to do things like compute the expected time taken by differentiating it. And you can go through this calculation and see that it does agree with what we computed earlier. And if you like, you can differentiate twice to get the variance and so on, although it does start to get a little bit messy. But if you have the time and motivation, you can go through and compute all this stuff. Everything is now systematic calculations using the generating function. With the simple idea of betting on a fair game, we have now computed the expected time for a sequence to randomly occur. We've computed its generating function, which gives us the full distribution. Okay, that's enough monkey magic for today. I did have lots more cool Martingale stuff to show you guys, from the mathematical definitions and important results and other applications besides waiting times. In fact, Martingale theory has many applications. A lot of stuff in probability theory, including foundational results like the strong law of large numbers, Radon-Nikodym derivatives, and much more. It also has uses in subjects which do not seem to have anything to do with probability, like harmonic functions, partial differential equations, differential geometry, Riemann surfaces, and more. But I think we've covered enough stuff to think about already for one video. So expect a follow-up to this, and also martingales may well pop up on this channel in other contexts. For now though, it remains for me to thank you for watching. Thank you. I hope you got something from it. If there's anything you would like me to cover in future videos, please mention in the comments section below. And of course, like and subscribe. I'll be back in less time than it takes a monkey to type abracadabra.